אפשר השאלה לבחינה זה חומר סגור לגמרי?
כן.
שום דבר, שום נייר?
נדמה לי שכן, לא, זה משהו בשנים קודמות. Okay. So today I would like to discuss the issue of two-time perturbation, which is kind of again global analysis, but of different type. And I will try to first to motivate the usage of this type of perturbation. And so to begin with, we will start with a very simple problem that you already are familiar with from the undergraduate studies, and then we will develop the theory. Okay? So the problem I would like to analyze for the moment is the equation, say x d dot plus omega 0 x equals some f, say force. Actually it should be force divided by m, but let's take m equals 1 cosine of omega t. So I hope you all are familiar with this problem. What is that problem?
Driven harmonic oscillator.
Driven harmonic oscillator, forced harmonic oscillator. Good. Without friction, right? It's just driven harmonic oscillator. You have a, swing, and you have a kid on the swing, and you apply force to the swing, periodic force. And what is the most important physical phenomenon associated with this equation, with this resonance? Okay. So we have to solve this equation. Let's say that x of 0 equals to x dot of 0 equals 0. That's the initial conditions. Okay. What we are going to do? So first of all, we know that the solution is a combination of the solution of the homogeneous equation plus a particular solution of the inhomogeneous equation, right? So we can write x of t as a sine, say, omega naught t plus b cosine omega naught t plus special solution of the inhomogeneous part, right? Now, you can formally find the solution for the inhomogeneous part by using the technique of variation of parameters that we have mentioned, I guess, during this course. But for the moment, let's do that in the way we are doing it in undergraduate studies. So we are going to write x d dot plus omega naught x. Sorry, it's omega naught squared, of course. Right? Yeah. Plus omega naught squared x equals f e to the I omega t, which is completely kosher procedure once we agree that we will take the real part of the answer. As long as the equation is linear, we can always solve it in the complex plane and then take either the imaginary or the real part of the solution. Okay, and now this is, and clearly you know that the way to solve it is to assume that x is, say, e to the I omega t times some constant c. Maybe c is not good constant, let's take d, right? And this will give us, so now every derivative is just taking I omega out, so this will give us d times omega naught squared minus omega squared equals f. You see? And the e to the I omega t cancels out. We put it here. You see what I'm doing? That's no problem. Okay? So we know that d is actually f divided by omega naught squared minus omega squared. Okay? So this is the inhomogeneous part. Now we can write it explicitly. The general solution is this plus that, and now I have to take the real part of A with this D. So I have here F divided by omega naught squared minus omega squared times cosine of omega t. Okay, this is the most general solution of this linear and simple, relatively simple equation. Constant coefficient. Now we have to implement the initial conditions. Okay? So first of all, you can easily see that the second condition, velocity equals 0, implies what?
A is
Implies that A, this must be 0. Because if I'm taking derivative, the derivative is taking only omega or omega naught out. And then I will put t equals 0. So this and this will be 0 automatically, but this one must be cancelled. So A equals 0. After deciding that A equals 0, now I have to fulfill the condition that x dot of 0 is 0. Okay?
And I think you did it backwards.
What?
A is the derivative.
I decided that this is 0. From this, I decided that A must be 0.
Yeah.
And now I have another condition that x of 0 is 0.
Yeah.
This will determine B. And clearly, this implies that B must be equal to minus Z. So the solution for the problem with the initial condition is x of t is f over omega naught squared minus omega squared times cosine of omega t minus cosine of omega naught t, which is this. And clearly when t equals 0, it is 0, and the derivative is also 0, so everything is fine. Okay? This is the most generic solution of this equation. Now, what will be, okay, so this is a general solution, and now the question is what's happened as omega approaches omega naught, right? So for the moment, okay, this to analyze this, we can write the solution as f times omega naught plus omega times omega naught minus omega. Okay, this is omega naught squared minus omega squared. And then we have cosine something minus cosine something, which, if I remember it correctly, is 2 times sine of omega plus omega naught over 2 times t, sine of omega minus omega naught over 2 times t. From the trigonometric identities that I never remember, but I looked at it yesterday and I hope that...
Maybe it's supposed to be minus.
What?
Maybe it's supposed to be minus. Minus before.
Where the minus? Here?
In the formula. But
Here?
I think yes, I will check.
Whatever. Okay, maybe there is a minus here. Okay. Now, okay, so again, this equals that. This is an analytic, different analytic expression of the same thing. There is no approximation here. But now I would like to approximate it when omega goes to omega naught. And my approximation will be that omega plus omega naught, I will write as 2 omega naught, or 2 omega, who cares, right? And omega, by the way, this is omega naught minus omega. And omega naught minus omega will be written as delta omega. This is a small parameter. Okay? I have a small parameter. What I obtained? I obtained minus 2f divided by, okay, so the 2 cancels, divided by omega naught, because this is 2 omega naught. Sine of omega naught t, this is that. Okay? And now the rest is sine of delta omega over 2t divided by delta omega. That's the approximation. Is that an approximation?
No.
Yes.
No, it isn't an approximation. That's just,
Yes, because I approximate omega plus omega naught by 2 omega naught.
well, that's not an approximation, really. You just
Okay.
said it.
Fine. Okay, this is the solution. Okay, now, the first part is just sine function, right? And now the question is how this thing behaves as delta omega goes to 0. So you see that as delta omega, it's not enough, importantly, it's not enough that delta omega goes to 0. What is the actual condition? I want delta omega t to be small. You see? It's not enough that delta omega is small. I need that delta omega t will be small. If delta omega t is very small, then I can approximate sine x by x when x is small, the delta omega cancels out, and I will have T there, pure T. Right? So again, I will write it.
But isn't T a parameter that goes from minus infinity?
From 0 to infinity, you have initial conditions at 0, right? So if delta omega times T is much smaller than 1, then the solution is x is f over omega naught times sine of omega naught t times, maybe I have a 2 here or something, times t. You see? And how this looks like? This looks like that. I have t is something like that. And inside t, I have this sine omega naught t. So I have, this is a resonance, right? There is no damping here, so energy is accumulated in the spring or the mass spring system, and I have a solution that grows to infinity this way. The envelope is going linearly, and this is going to infinity. Okay, this is the standard resonance in now. Remember that if delta omega is 0, perfectly 0, this is good, this condition is always fulfilled. But once I have even a tiny difference in delta omega, if delta omega is epsilon, then this solution will be valid until t is 1 over epsilon, right? And when t is larger than 1 over delta omega, then I should use this solution. And this solution, this implies that I have something like that. And this is going like this. Okay? That's, this is how the solution of this damp oscillation looks like. Now, when the t appears here, right, not in a sign or in exponent, but appear a naked t here, this is such a solution is called secular solution, right? Because I mean, the word secular is very weird because it means both non-religious person, right, and something that goes. And weirdly enough, the two, these are two opposite meanings of the same Latin root. So it's like lekales in Hebrew that carries both two opposite meanings, like to praise and to make fun of. One of them percolates from Greek, but secular in Latin means something like era or epoch or something like that, big chunk of time. And on the one hand, it was developed as something that is under the government of time as opposed to holy things that are eternal. And this is secular in the sense of not clergy or not. And in physics, it developed into that, which is something that goes to infinity. So, weirdly enough, that's okay. What I would like to stress is that to emphasize is that this is not a peculiarity of this equation. As a matter of fact, each time when I have differential equation with constant coefficients, right? Every differential equation with constant coefficient of this kind have solutions of the form e to the alpha 1t and e to the alpha 2t, right? And then if you remember, then if you now add some function of t here, right? As a, what's it called? As a homogeneous term, right? Then according to the variation of parameters, you have to write something. You have the Wronskian, right? The Wronskian is e to the alpha 1t, e to the alpha 2t, e to the alpha 1t times alpha 1, alpha 2 e to the alpha 2t. So the absolute value of that. And what's important, okay, and then you have something like e to the alpha 1t integral dt e to the alpha 2 tau f of tau over the Wronskian, things like that. And the important is, what's important is that, sorry, alpha 2 tau f of tau, that if f of tau is e to the minus alpha 2 tau, for example, right, then this thing is a constant, and the derivative, the integral with respect to t gives you a naked t, right? So you have t, maybe t times e to the minus 2t, so it shouldn't diverge, but once you have this naked term, then it's called a secular solution, and if essentially here it's I, so if you have something that oscillates here, then you have this phenomenon. So this phenomenon happens every time when the inhomogeneous term contains the frequency that is a characteristic frequency of the homogeneous equation in this sense. Not necessarily frequency, yes, because it may be real. So but when it's imaginary, then you have the coefficient is oscillating. So you have something that indeed goes to infinity. Okay. So once we, what the hell is that? Oh. Good, I printed the wrong. Fine. Let's hope now that it will work. Oh no. Okay, the wrong notes. I hope it still work. Let's see. Fine. So after all this long introduction, let me now show what's the relevance of this to perturbation theory. So let's consider the following equation now. X d dot plus x plus epsilon times x cubed equals to 0. First of all, what is that? What physical system is satisfying that?
Again, x cubed.
It's our beloved friend, the anharmonic oscillator, right? This is a harmonic oscillator, and here we have added, harmonic oscillator depends on Hooke's law. It implies that the force is proportional to the displacement of the spring, say, from its equilibrium. But Hooke's law is an approximate law, right? If you stretch the spring too much, then it will not satisfy Hooke's law, and you will have terms like that. Okay? And we have this epsilon, and now we want to find, and again, okay, I should supply you with the initial conditions. So the initial conditions are x of 0 is 1 and x dot of 0 is 0. These are the initial conditions. Okay? And how did I teach you until now what to do? Okay, so the general scheme of global analysis that we presented through this course is to say that x is equal to sum from n equals 0 to infinity of xn of t, some functions, times epsilon to the power of n. So for example, the first terms will be x0 of t plus epsilon x1 of t, okay? Plus epsilon squared. And then we plug it here, right? And we solve order by order in epsilon. So what will be the first, the zeroth order equation?
Harmonic oscillator.
Harmonic oscillator, yes. So x naught the dot plus x naught equals 0. And you remember that in this stage is also the stage where we implement the initial conditions. And in all other stages, the initial conditions will be, so x naught of 0 and x naught dot of 0 should be 0 and 1, and all the others are 0 and 0 and 0. Okay, so can you tell me what is x naught of t? The general solution here is a cosine t plus b sine t. Okay, and we have to satisfy these boundary conditions, which implies that the sine is 0 and the cosine the coefficient 1. So x naught of t is cosine t is what satisfies this condition. Yes, good. Now we go to first order in epsilon. We collect terms that are first order in epsilon. What are these terms?
x1 at the time
x1 double dot
plus x1
plus x1
plus cosine times z
equals minus cosine cubed of t, because this is x naught squared, x naught cubed. Okay? Now we have to use a formula for cosine cubed. What is cosine cubed of t? And so cosine cubed is, okay, and this is minus 1/4 cosine 3t minus 3/4 cosine t. Okay? And now we are in big troubles. Why we are in big troubles?
2 omega.
What?
With 2 omegas. What's this? Frequencies.
We have the standard harmonic oscillator, the homogeneous equation, and now we have two perturbations. One of them is this one, and one of them is that one.
One of them is the
Why are you in troubles?
one of them is the resonant frequency. One of them has the same frequency.
Very good. One of them is in the resonant frequency, and it will give me something that will grow and grow and grow to infinity. Which is a dangerous term? Who is the criminal?
This cosine t.
This one. Okay? Okay? Because here omega naught squared is 1, so this one is a term that leads to a resonance. And it will give us x1 that grow to infinity without bound. Okay? Could it be true that x1 grows to infinity without any bound?
No.
Why not?
Physically or not? Physically, just no spring will become eventually strain will.
But suppose that the spring is ideal. I mean, now we are saying once the spring will be so stretched, this equation will fail.
Yeah.
suppose this equation will not fail. Still, this system conserves energy. Right? You can write it as x d dot equals minus dou v dou x, where v is x squared over 2 plus epsilon x to the 4 over 4. Right? So it has an energy. So you can write it, the potential starts as quadratic and then get some epsilonic corrections, x to the 4. But if you started here at a certain potential energy at x equals 1, so you started here, then you go to here. There's no way that your displacement will go to infinity, because then it will not conserve energy. So the whole trick that we have worked so much in order to assimilate during the semester fails on its face completely. Okay. And the reason is this ugly term that gets into resonance. Okay? Now, is there a solution to, clearly this cannot be the case. Actually, people are saying, I never tried that if you calculate more and more terms in the perturbation, not only epsilon to the 1, but epsilon to the 2, and epsilon to the 3, and epsilon to the 10, and epsilon to the 100, eventually all these terms will balance each other, and you get something which is finite, but there is no practical way to do that. Okay, so we have to develop a different approach that will make us guarantee that we will not encounter such terms. This is the goal of the two-time perturbation theory. Okay? Any questions? No. So, here is the trick, and I guess that we will have no time to develop it for more than the lowest order relevant perturbation. Okay. So what I'm going to do is to define, okay, this is the equation I'm trying to deal with. Okay? I'm going to define, however, to regard x not only as a function of t, but as a function of both t and another parameter that I will denote by what? By tau, and this is epsilon times t. Now, t and epsilon t are not two independent parameters, right? Epsilon is fixed. T and epsilon t are not independent, but from now on until הודעה חדשה, we will regard them as if they are the same parameter. They are two independent parameters, right? So from now on, we have two small parameters, so to speak, t and tau. And another thing is that we are going to replace every d dt, right, is replaced by dou t plus epsilon dou tau. See why? right? Again, the chain rule and ddt squared accordingly. Good. So in order to avoid the, well, okay, and so I will write x of t as z naught of t and tau, x of t and tau if you want, plus z1 epsilon z1 of t and tau plus epsilon squared z2 of t and tau, and so on and so forth. Please try to concentrate because, I mean, this is the next 10 minutes, I guess, are the essence of all this stuff. Okay? And I'm going to plug it here. Okay? So, what I'm going to get? X d dot. Okay? Let's write step by step. X. So x dot t. Okay, ddt of x is equal to. So I have dou z naught dot t plus epsilon dou z naught dot tau.
Can there be a half?
Why half?
Oh, okay, I see.
Plus epsilon dou z1 dot t plus epsilon squared dou z1 dot tau. You see? And so on. Next, what is d2x dt squared? This will be d2z naught dt squared plus 2 epsilon d2z naught dt d tau plus epsilon squared d2z naught d tau squared, yes, plus epsilon dz1 d2z1 dt squared plus 2 epsilon squared dt z1 dt d tau plus epsilon cubed d2 z1 d tau squared, and blah 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 blah. Okay, and now I would like to plug this here and to collect term by term in epsilon. Okay, what I will get for the zeroth order in epsilon. In epsilon. Yes, epsilon is a small parameter. I still use epsilon as the only small parameter, and I will collect everything that is a leading order in epsilon. So what do I have for epsilon to the power of 0? First of all, this term will contribute nothing because it has an epsilon in front of it, so it's epsilon to the power of 1. This term will give me what? Only that number. And this term will give me only the first in all this series. So I will get d2 z naught dt squared plus z naught equals 0. This will be the solution. Okay. What is this is the equation to first order in epsilon. What will be the solution?
Well, we only have its dependence on t, not tau.
Very good. Thank you very much. And therefore what?
Well, since the equation has no terms of tau, we see that it's two separate functions that are multiplied by each other.
Very good. So the solution is Z naught is A of tau, some function of tau that I don't know what it is, times e to the it, plus some, if I want it to be real, the complex conjugate e to the minus it. Right? This is the solution for Z naught.
Then we add a shouldn't we need to add a function that depends on tau?
Of course we need.
An arbitrary.
For the moment, we didn't find it. We don't know what A of tau and what A star of tau. Except that A star is the complex conjugate of A.
But why don't we have another function that's plus a b of tau? Like, is that not?
Why don't we have another function which is plus b of tau? You know, because then this function will appear here. Right? You will not satisfy that. You're not going to satisfy that. You see? Good. So this was the first order thing. And for the moment, note that I've forgotten about the initial condition for the moment. In this method, they appear at the end. They will appear at the end. Okay. Now what is the equation for first order in epsilon? Please. So we need for x d dot. What do we have here?
2 epsilon d squared 0.
I have this one
And the second one.
and I have this one. Okay? Let me do it like that. I will write it as d2 z1 dt squared, which is that. Okay? Plus, I will take the x. I have this. Right? So plus z1 equals to everything else I will put on the other side. Okay? Equals to minus 2 d2 z naught dt d tau, which is that. Right? And what is still missing? The cube. The epsilon times x cubed, which of course will give me just the z naught cube. So here I have epsilon, which I put aside because everything is epsilon, minus z naught cube. Okay? Good. This is actually all I need. So okay. Anyhow. Okay, so remind you, we're dealing with x d dot plus x plus epsilon x cubed equals 0, with the initial condition x of 0 is 1 and x dot of 0 is 0. Okay, now so now I have to plug z naught here. You see? Fine. So what I'm going to get is d2 z1 dt squared plus z1 equals to minus 2 times Now I have to take that note and to take one derivative with respect to t and one derivative with respect to tau. So this will give me I times dou A dou tau e to the I t minus I dou A conjugate dou tau e to the minus I t. You see? Make sure that you understand it, right? I took the derivative of this second derivative, one with respect to tau, that give me that, the derivative of A, and one with respect to t that give me I here and minus I here. Good. And now I have to, what's the next step? Minus Z naught cubed. What is Z naught cubed? Let's write it in all its glory, right? So it will be A cubed e to the 3it plus 3a squared A conjugate e to the it plus 3a conjugate squared e to the minus it plus a conjugate cubed e to the minus 3it. You see? Okay? Now the equation for that one is written in all its glory, and if we want, now we have to solve for that one. Okay? Now you are pretty sure that I am completely crazy, because who is the idiot that will try to do that? However, we are not going to work hard at all. All we have to make sure is that we will not have resonant terms. Okay? So we know that this equation is an equation that resonates with every inhomogeneous term with frequency 1. So who are the dangerous guys?
First, second, fourth, and fifth terms.
This is dangerous. Okay. This is dangerous. This is benign. This guy is fine. This is dangerous. This is dangerous. And this one is fine. Okay? So I have to make sure that all the dangerous terms sum up to 0. And this is a constraint on A of tau. So I'm using this constraint to determine A of tau, and this will give me the answer. We are not going to solve this ugly thing. All we are going to make sure is that we have no resonance. This is the condition. No dangerous resonance. Okay? Now, even better, note that the green terms are the complex conjugate of the red terms. So I don't have to satisfy the two equations. Once I'm making sure that the two reds add up to 0, then the two greens are adding up to 0 automatically. So all I have to do is to make sure that minus 2i dou A dou tau minus 3 A squared A star equals 0. This is all what I have to make sure. Very good. How do I do that?
It's kind of a Schrodinger equation.
The conjugate is what makes
It's
it.
a nonlinear Schrodinger equation, right? But no. We are not going to. No, we are not going to
Can we rewrite the term A in terms of like R e to the I?
Thank you very much. Oh,
That's not the way to basically make
we are going to write A as R of tau e to the I theta of tau. Okay, and then this implies that. First of all, let's write it as do A dot T, dot tau, sorry, do A dot tau is equals to minus 3 half, okay, times I times A absolute value squared times A.
And the minus should
And
disappear.
the minus should go. Okay? And now I make this substitution. So this will give me do R dot tau plus I dot theta dot tau times R is equals to 3 over 2 I R cubed. And the e to the I theta cancels. See? Okay. What I'm going to do with this equation, I will separate it into the real part and imaginary part because R and theta are real. Okay? So the real part and the imaginary part must be satisfied, each one independently. So this equation gives us actually two equations. One of them is do R, do tau is 0. That's the real part, meaning that R equals R naught. I started at a certain R, this is R for good. Okay? And the other equation is do theta do tau is
3 over 2
3
R
half
squared.
R naught
Squared.
squared, because this R cancels with the cube. Okay? So now I know that theta is theta naught plus 3 halves R naught squared tau. Here we are. So, with that, we know that what is Z naught. Now we can go back to Z naught. Z naught is A. So Z naught is R naught times e to the I theta naught plus 3 half R naught squared tau plus IT plus complex conjugate. This is the complex conjugate. Okay? So it's very easy. So it will give me 2 R naught because times cosine of theta naught plus 3 halves R naught squared tau plus T. This is Z naught, right? So after all, we found that Z naught is 2 R naught cosine of T plus 3 halves R naught squared tau plus theta naught. Good. Now, after doing that, I will implement the initial conditions. Okay? And, okay, what are the initial conditions? So, first initial condition is that at 0, I have 1. Okay? So, clearly, when t is 0, tau is also 0. So I have one condition which is 2r naught. Cosine theta naught must be 1. Now the other condition is x dot of 0 is 0. Now, dot, remind you, is dot dot t plus epsilon dd tau. But since I am at first order in epsilon, I will take only the dot dot t. Right? And if I'm taking the derivative of this with respect to t, what I will get is minus 2r naught sine of what? But now I have to sine theta naught must be 0. Okay, which implies that theta naught is 0. Which implies that r naught is 1/2. So, after all that, we can write the solution. We can write the solution.
Will it change anything if we set theta naught to n pi?
No, because the cosine is completely
It's a constant.
yes. So the solution is
So it would be minus 1 and 1.
x of t is 2r naught, but r naught is 1/2, so it's 1. So it equals to cosine of t plus theta naught is 0, but I have 3/8 because r naught squared is 1/4 times epsilon t. Or if you want, cosine of t times 1 plus 3/8 epsilon. So to the lowest order in epsilon, what is the effect of the nonlinearity? We introduced nonlinearity here, and what was the effect of the nonlinearity? To zeroth order in epsilon, the effect is without epsilon, I will get cosine t. This is what I obtained for the unperturbed equation, right? And now with epsilon, to the leading order on epsilon, what it does, it just change the frequency. Instead of omega naught equals 1, our omega naught is 1 plus 3/8 epsilon. Right? So the time, how do you say? The period is 2 pi over omega, so the period gets shorter. And why it gets shorter? It gets shorter because, remind you that if this is a pure quadratic thing, what I have added is epsilon x to the 4, so it goes like that, right? So it's the first order. All I obtain is change in the frequency. You see, but let's stick to the mathematical trickery, not to the physics. The mathematical trickery is the zeroth order is trivial. And then you use only from the first order, you use only the condition that you don't have resonances in order to determine A, and that's the end of the story. Okay, so now that we are all expert on two-time perturbation theory, let's do
Can we make any intuition for when x for when the cubic term comes with a minus sign. Is there a way
Hmm?
to equation? If we were to put in the differential equation a minus in the last term,
No, that's too bad.
yeah,
Because this implies that your potential
it's a W.
looks like that. It's unbounded from below and then goes zeros, right? But in quantum physics, it's a completely horrible thing to do. Although people are doing that to calculate quite many things, but not.
Looks like frog face.
Hmm?
Looks like frog face.
Looks like
Frog.
frog.
Yeah.
Do you see that frog?
There's 2 eyes and
Except that it's green. I mean, I don't see it.
It's like the highest, the
Yeah.
top of the head. It's
Of
like
the frog.
the two eyes.
The ears. So
Yeah.
That is the eyes.
whatever,
Eyes.
whatever the frog has. Okay, fine. Okay. So after we have we got an experts on that, let's implement our analysis to something else. If I will write here that, what is this physical system? What? It's a damping term. So what I will get oscillations that are decaying very slowly because of this epsilon, but they will decay to zero. Eventually they will decay to zero. And we know that they will decay how? Exponentially, like e to the minus epsilon t. That will be the general behavior. You have oscillations that decay, and there is an exponential within an exponential. Okay. So here we are. Okay. We put a nonlinear damping term. We put a nonlinear damping term, and my question is, מה נשתנה? What's the difference between what of all what we did until now, right? For the problem with x cubed, what will be the difference now if we have x dot cubed? So clearly this remains the same. So the zeroth order do not involve the epsilon term, right? And this is replaced. So now we, instead of having z0 cubed, I should replace this, right? By what? I have a minus, and I have the epsilon, and I have the z dot z 0 dot t cubed. Okay, this term is the same, this term have changed. If I'm going to this monster, you see, what is going to be changed? What? The final part, because now I have to take the final part, because now I have to take z dot z0 dot t, which is ia e to the it plus minus ia star e to the minus it, and this is what I have to raise to the third power. Okay, but I would like to claim that, okay, so first of all, I will have an I cubed in front of everything. I cubed is minus I. So I should replace this minus by plus I. What else? I have a minus sign between the first and the second, and clearly this implies that this is plus, this becomes a minus, this is plus, and this becomes a minus. Still, the dangerous terms are the green and the green and the whatchamacallit term. You see? So the only difference is that now what will be what is the condition for no resonance? The no resonance condition is minus 2i dot a dot tau. I'm doing it with the green, with the yellow red terms, plus I minus 3i a absolute value squared a equals 0. So actually the only difference is that now the I cancels out. And we have dot a dot tau is minus 3/2 absolute value of a squared a, which implies that dot r, now dot r dot tau plus I dot theta dot tau r equals minus 3/2 times r cubed. And now you see that separating this into real and imaginary part, what I will get is theta dot tau is 0. So theta is theta no, right? And dot r dot tau is minus 3/2 r cubed. Okay. So what? So dr over r cubed integral from r naught to r of tau is equals to minus 3/2 times tau. So I've integrated already. And this now what is that? This is 1 over, so this is r naught r of tau of 1 over 2r squared with a minus sign. Am I right? Let's check because I brought the wrong notes. So this is 1 over 2r naught minus 1 over 2r of tau. Squared. Yes? Equals minus 3/2, minus 3/2 tau. Okay? Which implies that I want r of tau. Yes, this is my goal in life. So what can you tell me? What is r of tau? What is r of tau, please? So
Plus minus
1 over 2r naught squared plus 3/2 tau is equals to 1 over 2 r of tau. Right?
Squared.
Well. Now, I have 2r naught squared here, and I have 1 plus 3 r naught squared tau. Is that? So now the 2 and 2 cancels out, and I find that r of tau is r naught divided by the square root of 1 plus 3 r naught squared tau.
Plus minus, no?
No, you have to take the plus. Okay. So I have the solution. I have that note. Okay. So what is the solution now? Okay, I'm taking the risk of erasing everything, hoping that I didn't do a mistake. But it doesn't matter so much. So now what is that note? That note is A is R e to the I theta. E to the I theta is trivial, is e to the I theta naught, right? And I have this R, so I have R naught divided by square root of 1 plus 3 R naught squared tau times cosine of t plus theta naught. Okay, now I have to implement the initial conditions to find what? To find R naught and theta naught. These are the things that I would like to find. So suppose my initial conditions are x, okay, this is x. X0 is 1 and x dot of 0 is 0. So for x dot of 0 to be 0, if I'm taking the derivative with respect to t here, all I have is I will have sine of theta naught, and I want this to be 0, so this implies that theta naught is 0. And then I want R naught to be 1 to satisfy that. So x of t, finally I will replace tau by epsilon t, and I will get x of t is cosine t divided by square root of 1 plus 3 epsilon t. So you see that it also goes to 0 because I have damping. Right? I started by taking the spring to 1 and no velocity, velocity is 0, and I release it, so it goes back and forth. Without the damping, it will go back and forth to infinity. With the damping, you see that as t goes to infinity, this is going to 0. However, instead of going to 0 like exponentially, like e to the minus epsilon t, which is what will happen if we have a linear term here, instead of that, it goes like 1 over square root of t, much slower. And it's much slower because the friction is decaying very fast with the velocity. Right? You can see it if you drive a car and you see a traffic light way ahead of you, right? But it's red light, so you want to stop. In many cases, you just take your leg from the gas, not pushing the brake, but lift your leg from the gas and say, okay, now I have a friction, so I have to slow down. And you should notice that when you slow down, usually you do not estimate it correctly. So instead of arriving at the traffic light at almost zero velocity, you also arrived it at a substantial velocity, and then you have to brake. And the reason is because the friction is non-linear in this range of velocities. The friction is non-linear with the friction comes mainly from air turbulence that your car is generating, and this is going like velocity squared, velocity cubed, so something like that. Velocity cubed is, I think, typical for airplanes or aviation. But in any case, this is a kind of thing, and then it slows down, but it doesn't slow down exponentially, but as you go with smaller and smaller velocities, the effect is going very fast to almost zero, and that's the reason why you miss the correct, distance, and you have to hit the brake at the end. This is not, of course, if you go at a very, very, very slow velocity, then it will be linear friction, because this is stock slope. If you remember first year, you release balls of something into glycerin, and you measure the stock slope, but this is only for very small velocities. Okay, so my last example for today will be yes. What is that? Equals zero. So, what's the physics of this system? This is first derivative, right? What physics you see here?
I expect dampening when x is greater than 1.
Wait, just to help myself, this is x0 is 0, and x dot of 0 is 2a for whatever reason on Earth. Right? Physics, what is that?
There's a competition between damping and yeah.
This is the harmonic oscillator, right? Now, this is a damping term, linear. However, what's the sign of this term?
It depends how large x is.
Yes. If x is very small, then you have negative damping, right? Yes, and if x is large, you have positive damping.
So it seems that it should balance out, should eventually reach the amplitude equals 1.
Exactly. So essentially what you have here, if this is x and this is x dot, right? Then you start here, you go out, and then you stabilize on a certain value.
And what happens if you start?
This is called the limit cycle, right? And this system is known as a van der Pol oscillator. Pol with double L, who knows?
If we change the initial conditions, we will go inwards, right? Until we get the cycle.
Literally, if you start here, you will go like that. So that's a limit cycle. Limit cycle attracts you to a cycle, right? It's something that you never encounter. It's very common in nature. Okay, common in nature. You never encounter it in the undergraduate physics studies because
It's a chaotic system.
no, it's not chaotic. It's limit cycle. Limit cycle is not chaotic.
Non-linear.
It's an effect of nonlinear dynamics, but there is no Hamiltonian system will give you that, right? It must be dissipative. And since undergraduate studies are concerned on conservative systems, you never meet these things. And unfortunately, we don't have mandatory or even non-mandatory course in nonlinear dynamics during the undergraduate studies, which is, I think, a shame, but
Isn't there like a third-year course that's also?
Sorry?
Isn't there a third-year course that's also like the master's course? Sometimes I think.
And go.
at the end of the day, people who end up the third year here usually have no idea what a fixed point is. Which is quite bad. Okay, so again, all we have is all the machinery that we already have. Okay, so what do we need now? So this term will remain the same. I mean, this will remain the same. No need to do it again. This will remain the same. This will remain the same. The only difference is here, right? So now we should put here. We should put here. Do z naught do t times z naught squared minus 1. Okay, so let's erase this. So this is that, and now we have to multiply. Okay, so let's start. So do z naught do t. This is IA e to the it plus minus IA star e to the minus it, right? And this is that's not squared minus 1. This is what? This is a squared e to the 2it plus, okay, let's write it. So I have overall minus here, and now I have IA e to the it minus IA star e to the minus it times a squared e to the 2it plus 2a absolute value squared plus a star squared e to the minus 2it minus 1. Okay? Dangerous terms. This and that, of course. Now, who are the terms that will give me? Okay, first of all, let's forget about the e to the minus, because we see that it's a real function. So if we satisfy it for the e to the minus, we satisfy it for the e to the plus. So we have here minus 2i do a do tau. This is this term, this dangerous term. What are the others?
Minus I, A star, A squared.
First of all, we have this times 1. This will give us
And
plus.
well, it's also times 2a squared, 2 absolute a squared.
Yes. So, okay. So minus I A times 2 absolute A squared A minus 1. Okay, which means this plus that and that. Anything else?
Yes.
The first term, right? The I A star times the first term in the.
Wait. We took this with that and that.
And the second term would be
Now, this
Exactly.
times that
Exactly.
is also a dangerous term. So this will give me what? Minus and plus. I have plus I times absolute value of A squared times A. That's it. Okay? So this and that. Anything else?
No.
I think not. That's it.
Let's see.
That's it. Good. So again, the I goes away. And what I have is the A dot tau is equals to 1/2
Minus, shouldn't it be minus 1/2?
wait. 1/2 times
A
A
absolute value.
minus A squared A. I hope. Am I right?
And minus.
No, it's because he's swapped.
No. There are two here.
Minus plus 1.
This one, there are two here and one here with opposite signs.
Yeah.
Okay? So yes. This is that. And now, if I'm writing again A as R e to the I theta, both R and theta are tau dependent. What I will have here is, so you see that the theta term, the dot theta dot t will have, so theta must be constant because everything is real. And we have the R dot tau is 1/2 R minus R cubed. Which is good. You see, it implies that it goes at the beginning and then it separates. Okay? And theta dot is 0. So again, so theta is theta naught, sorry. Theta is theta naught, sorry. And now what is the solution for R? Please check that the solution is R equals R naught divided by square root of R naught times 1 minus e to the minus tau plus e to the minus tau. So first of all, when tau is 0, here I have 1 minus 1, and here I have 1, so it's R naught. You see? And when tau goes to infinity, then e to the minus tau is 0, and
It's square root of
Square root of
R.
I will have square root of R naught of course, because it's R naught squared. Yes. Okay? So when when tau goes to infinity, I will get 2. So essentially the solution will be x equals to, I should plug it here. Now it's the third time we are doing that, so I will cut corners. X equals to R naught divided by square root of R naught squared times 1 minus e to the minus tau plus e to the minus tau cosine of t plus theta naught.
Wait, shouldn't in this case it be sine already? Because of the initial condition.
Yeah, okay, so theta naught is pi over 2, if you want. Okay, so you can take it to be sine, right? So and now we want to implement the initial conditions, so this should be 0, so theta naught is pi over 2 or minus pi over 2, whatever you like. So this is pi over 2, and then you want the derivative, or let's write it as time t. Maybe I'm doing something wrong with the signs here, but who cares? And now x of x dot will be, the sign is becoming cosine, so it's 1. So x dot is simply that, and I want this to be equal to 2a. So I want R naught to be equal to 2a. That's it, right? That's so I discovered that x is 2a sine t divided by 4a squared 1 minus e to the minus epsilon t plus e to the minus epsilon t square root to the power of 1/2, right? And this converges to 1 as epsilon t goes to infinity. Note that it converges exponentially to the limit cycle, right? We'll start whatever here, and it converges exponentially to a limit cycle of radius 1. That's a Van der Pol oscillator, very famous. People are implementing it using all kinds of electric circuits that have something that looks like negative friction, and that's it. Okay. So this is the 2 time. I mean, in general, okay. We gave 3 examples. Of course, there is an infinite number of examples one can give. A very important case that I didn't consider here because it's slightly more complicated and it requires a lecture by itself is a parametric resonance. So, like if you have your child is riding a swing, right, and you push him or her, then what you are doing is force oscillations. And because you don't push, you just wait him to arrive at you and before you push, right? You're not doing something like that, but you stand here and every time the swing is coming, you give it a push. So you lock yourself into the resonance because the frequency of the push is exactly the frequency of the spring by definition, right? I mean, it's a train of delta functions, but if you will take the Fourier transform, you find that most of the amplitude is in the frequency of the swing, right? So this is standard resonance. However, if you are too lazy and the kid is mature enough, So you want to teach him to ride the swing, but by doing something like that, right? Taking his or her legs up and down. How does this work? Quite tricky. Because you know that the center of mass is not moving under the action of internal forces, right? So this is parametric resonance. This is like having such an equation. So x d dot plus omega naught squared times 1 plus epsilon cosine omega t x equals 0. Why is that? Because when you the omega naught of the swing is square root of L over G or something, right? And when you take your legs up and down, you change L. So you change L periodically, so you add a slight periodic modification to the omega naught, right? And if you're doing it in the right frequency, which is not the frequency of the omega naught, but half the frequency of half omega naught, then you have an instability. You see that x is 0 is always a solution, but you have an instability, it becomes an unstable solution. This is called parametric resonance, and the way to analyze it is to use this machinery. You can read about it in the book of Benner and Orsag, of course. And by the way, perhaps you don't know, I'm sorry for wasting your time, but it sounds interesting. If you switch your legs fast enough in the right manner, you can stabilize the swing upside down. Capizza pendulum, yes. So you can have the swing like that, and if you I don't think that one can do that with legs, but there are ways to do that, right? So this is known as Capizza pendulum, and this also have all this is in the theory of parametric resonances, but we are not going to go into it. It's a fascinating, there's a fascinating physics here, but that's it. Okay, so see you next week.
Thank you.
היה פה פעם בקולקטיום למישהו שעשה הדגמה של קפיצה פנדולום. נדמה לי זה לא הצליח לו, אבל הוא ניסה. בעצם כל פעם שאתם מנסים נגיד לאזן מטאטא על היד שלכם, כן? תנסו פעם ותשימו לב שבלי לחשוב אפילו אתם עושים ככה. זה בדיוק זה. אוקיי.
תודה רבה.
תודה רבה.